Today I will talk about the Ocean Color Operational System, which is part of the Copernicus Marine Environment and Monitoring Service, which I think you have heard about during these days. So this is the outline of my lecture, which is basically made of 4 main topics. I will first introduce you to the Ocean Color Thematic Assembly Center, which is part of the CMEMS. It is actually the CMEMS component, the Ocean Color within CMEMS. Then for those of you not familiar with Ocean Color, I will try to give you some basic concepts that will allow you to be more into the next 2 main points, which is the level 2 to level 3 satellite processing and the level 3 to level 4 satellite processing steps. So the Ocean Color Thematic Assembly Center is a distributed system which acts as a production center of high quality products, ocean color products. It provides the operational service for 2 CMEMS, and currently it is made of 3 production units based in Italy, where I'm from, in France, and from the UK. Each of these production units is in charge of 1 or more of the ISAC regions, which are the global, the Arctic, the Atlantic, Baltic, and Black Sea. And today we will focus mostly on the Mediterranean Sea. So the CMEMS OCTAC basically downloads data from the space agencies, check them for quality before ingesting them into the global and regional processing systems. Then the outputs are also quality checked before being stored and disseminated to users. So basically the OCTAC stands as a kind of a bridge, stands between the space agencies and you guys. 2 main product areas are available from the CMEMS website, which are the ocean optics, which is the remote sensing reflectance. You have heard about it from Pierre-Yves this morning. The KD, the attenuation coefficient, and the IOPs, the inherent optical properties. We'll talk about this later. And you can find them under the turbidity, transparency, and reflectance tags from the CMEMS website. And of course, the ocean chlorophyll, which is the probably most known parameter you know from ocean color. The one we provide is a multi-sensor and multi-water type. So which is it is kind of difference of what you can get from space agencies websites. Products, and so the names or codes that you can find on over the websites may differ according to the time with which they are made available to users. Which is the near real time, the delayed time, or the reprocessed data. The near real time is the data processed with preliminary or any ancillary data and are generally available the same or the next day as the satellite overpass. The delayed time, the delayed time are processed with the final ancillary data after a few days, as soon as they are made available from space agencies. They both cover, let's say, the past 2 years' time, generally. Then we have the reprocessed data, which are produced generally once a year, updated once a year, and are produced with a unique configuration of the processing chain. Generally, this happens when the calibration and validation can afford and improve the products. The reprocessed data cover the entire time series. Here you can see the satellite constellation we deal with, which is the Seaweeds, Meris, both passed away. Aqua still alive, Vers and recently Olsi. We can distinguish also the processing level among sensors, among products, sorry. we generally have the level 2, which is the input data from the space agencies, and the level 3 and level 4, which are the output of the processing chains. They're both geophysical products. In our case, it has to do with 1 kilometer and daily resolution for both type of levels. The level 3 is, let's say, only about the combination of all the satellite SWOTs, while the level 4 has to do with gap filling. So yeah, we use interpolation. So let's move to the ocean color basic concepts. As we say, as you know, light emitted from the sun interacts with the seawater and its constituents, which are basically phytoplankton. We can measure phytoplankton through the chlorophyll concentration, the suspended matter, and the color dissolved organic matter, before being eventually captured by remote sensing, obviously through the atmosphere. You have heard about the difficulties of going through the atmospheric correction step. So the ocean color is the description of the optical properties of the medium through which the light propagates. The ocean color is basically the inference of the characteristics, which is the quality and the quantity, who and how much, of the water and constituents from their optical signatures. The optical properties of the ocean are conveniently divided into two main classes, the inherent and the apparent optical properties. The inherent optical properties, the IOPs, are those basically depend only upon the medium and its constituents, and are therefore independent of the ambient light field. These are the absorption and scattering. They're both made by the additive contributions of the single elements. For example, we have the seawater particles, both phytoplankton and non-algal particles, and the sea dome contributing to the absorption, and the seawater and particles contribute to the scattering. Actually, from the remote sensing point of view, we are basically interested to the backscattering, which is the part of the scattering that is reflected back to the sensor. The apparent optical properties, on the other hand, depend both on the medium and hence on the IOPs, and on the geometrical, which is the directional structure of the ambient light field. It is important for them to display enough regular features and to be so that they can be useful descriptors of the water body and hence of its constituents. Among them, we have the spectral downwelling gradients, which is defined as the total amount of light reaching a surface area element from all the upward directions. This is a cast we took a few years ago, not so far away from here, ED cast, and as you can see, it decreases with depths according to Lambert-Beer law, but not all wavelengths decrease the same way at the same rate, and this depends from the KD, which is the attenuation coefficient from the downward irradiance, and describes the rate of change of ED with depth. It has units of meters at to the -1. Basically, the smaller KD, the higher the water transparency. The bluer is the water. This is a KD spectrum, and you can see that the ED decreases faster, goes faster to 0 in correspondence of high value of KD, which is here. Two important parameters can be derived from the spectra, from this profiles. The Euphotic Depth, which is defined as the depth at which ED falls to its 1% subsurface value, and the penetration depth, which is roughly 1/5 of the Euphotic Depth. and identifies the layer mostly contributed to the signal captured by a remote sensor. So in this case, we have a euphotic depth of roughly 65 meters and a layer contributing to the remote sensing to the ocean color of about 15 meters. And this is a ED spectra from discussed. Another important parameter is the upwelling gradients, which is defined as the amount of light reaching a surface area element through one solid angle and coming from below. This is the same cast. You should notice the order of magnitude difference between the LU and the ED, and this is a spectrum. When we combine these two measurements, we have the remote sense reflectance, which is defined as the ratio of the LU over ED. This is the spectrum. And yeah, in the area, you can see that the water was quite bluish with the maximum at 490. An important point is that remote sense reflectance is also proportional to the IOPs through the ratio of BB over A plus BB. So this will come next in the lecture. An important parameter is the maximum band ratio, which is used within the algorithm developments very, very often. And it's defined as the maximum reflectance in the blue over the green. The reflectance in the green is chosen as it doesn't vary a lot with the chlorophyll concentration. So it's taken as a kind of reference. And these are the quantity that interest us. This is a very common chlorophyll profile over the same station with the euphotic depth, the penetration depth, so the layer contributing to the satellite signal. And this is basically the chlorophyll that, the chlorophyll as it will be measured from a remote sensor, which is basically the chlorophyll profile weighted by the attenuation coefficient of light. So the contribution of chlorophyll decreases with depth from the remote sensing point of view. An important point is that okay, ocean color is an important tool, is a very effective tool, but gives you a layer much thicker than the SST, for example, but still you can miss very important features like the DCM, which is in this case varies as a factor of 5 as with respect to its surface value. So an important concept in ocean color is the difference between case 1 and case 2. In case 1 waters are generally the waters where the optical variability is well explained by the phytoplankton abundance, and which is chlorophyll, not generally associated with open ocean. Contrary to the case 2 waters, where the sea dome and the suspended matter can play a significant role, are generally associated to coastal waters, and so that the phytoplankton only partially can explain the optical variability. Okay, let's move to the level 2 to level 3 satellite processing. The processing is made basically of 4 parts: the data download from space agencies, the single sensor pre-processing, which is very important, then we have the sensor merging, and the geophysical product retrieval. The processing chain that I will talk about now is basically about MODIS Aqua and VIRS, as OLSI is still not included in the processing chain, simply because it's not mature enough for being considered operational, although it is on its way through. The first step is so after data are downloaded from the space agencies, the first step of the single sensor pre-processing is the destriping. So both Aqua and VIRS scan the Earth via a rotating mirror system, which reflects the surface reflectance to band detectors. The point is that we have two hardware problems that both gives rise to the stripes that you can perhaps see in this snapshot. Can you see them? Like here, perhaps not them, not so much, but still they're there. And so they give rise to this to the stripes because the two sides of the mirror are not exactly identical, and the band degradation, the detector degradation, is not homogeneous. So we have a features which has really nothing to do with the oceanography of the scene you are looking at, but it's simply another problem. We generally, we operationally delete these stripes. We correct for the stripes using these methods, basically by the Michelson et al. Paper on 2014, which uses the use a detector as a reference, and by computing the PDF of this detector, of all the observations in this detector, and by applying a bias correction of all the other detectors to this one. Another problem is given, this is only about VIRS data, is that, and is simply given by the very large field of view of the sensor. The sensor detectors have a constant angular resolution, so that the sample area increases of nadir. So the result is that you have a bow-type shaped sequence of acquisitions. So space agencies remove these effects, as you can see here, remove these effects through a combination of aggregation and deletion of the overlapping pixels. And so it results that at the edges of the scene, you have all these lines, so all these rows of missing data. Within the operational processing, we remove this by linear interpolation. An important point, perhaps the most important within the single sensor preprocessing, is the flagging system. Each level 2 granule is quality checked via the application of these level 2 flags, which are output together with the level 2 files from the space agencies. These level 2 flags are simply coded conditions of the acquisition, of the single pixel acquisition. So you will be able to discard all the coastal pixels, for example, or all the pixels affected by very thin clouds, which you can still look through, but still the quality of the product is not very high. Afterwards, we remove all the isolated pixels, and the same way we fill all the isolated pixels which are surrounded by good observations using the near neighborhood approach. Then all the available granules for each day are remapped over a regular grid, and they're combined together into single files containing the remote sensor reflectance at nominal sensor wavelengths. So this table shows the wavelengths and each sensor, and you can see, for example, the 443 here, this line, which is common to all sensors. So before being able to merge the single sensor's contribution, they need to have the same measurements at the same wavelengths. So the 443, it is common to all the others, while, for example, there are others, the 410, 412, and 413, which varies of a few nanometers for each other. We use the band shifting approach, which consists of the application of the quasi-analytical algorithm in both forward and backward modes. As I was telling you, the remote sensor reflectance is a function, is proportional to the IOPs of the medium, of the seawater. So starting from the remote sensor reflectance at the sensor native wavelengths, this algorithm allows you, through the characteristic spectral shapes of the IOPs, to estimate the IOPs at the target wavelengths. So we can use a common set of wavelengths for sensors. And this is possible with uncertainties below 5%, which is a very good result. Now we have all the ingredients for merging the sensors. So these are two snapshots from Aqua and VIRS. It is the remote sensor reflectance at 443. So three possible conditions can happen. The pixels or the area is observed by both sensors, or only one of those was able to look at them, or it is discarded by both. So in the former two conditions, the method is not really straightforward because it strongly depends on the ability to reduce the inter-sensor bias to zero. When the pixel by the area is sampled by one sensor only, or by the surrounding pixels by more than one or by other sensor only, then there is a high probability of introducing artifacts which has really nothing to do with the scene you are looking at, but rather with the method you are applying. So to mitigate this problem, we use the climatology and together with an ad hoc smoothing procedure to fill in the missing original observations. So we have the common climatology, which is used to fill both gaps of the two scenes. And in this way, the average of the two fields is easily computed. Consider that in this case, we consider that the interbias sensor of the two is 0. But perhaps in the future we will try to characterize better this behavior, which has to do with the longer time series and so on. Obviously, at the end, all the non-observed pixels are taken off. So, and this is the merged products. So once we do this for all bands, an important point is that features which are only present in the climatology, for example here, or the reddish area in the climatology, which was not really present in the scene, is also absent from the merged products. So the climatology doesn't really add let's say, geophysical variability to the outcome. Once we do all this for all bands, we ended up with a remote sensing reflectance spectra. This plot shows you the RRS for 4 lines. The blue and red are the MODIS and VIRS only, so the single sensors spectra. The green one is the multi-sensor, and which are both the 3 of them taken in correspondence of this in situ observations. These are a few examples, and you can see that the agreement is quite good, apart from perhaps this one, which is the last one. But an important point is that, in blue here is shown the area only sampled by MODIS Aqua. In red, the one only sampled by VIRS. In green, the combination of the two. But you can see that all together makes the the merged product. So you will see that there is a significant increase in the number of the observations. And this is an estimate of the how good is the merging with respect to the in situ observations. So all of them underestimate the in situ observations, but still the green doesn't really add any significant source of error. Now we're ready for the geophysical product retrieval. So this plot shows you the maximum band ratio between the blue and the red and the green, sorry, versus chlorophyll. All these plots were taken in the Mediterranean that gave rise to the algorithm functional form, the black line, which is coded here, as opposed to the global standard from the Space Agency, from the NASA, which is the other line. And from this plot, you see the need of regionalizing the algorithms, which, from which you can see that there is a clear overestimation of the chlorophyll when you would apply this line with respect to this other one. And this is the algorithm functional form, which is for case 1 waters only. This other one is instead the case 2 water, which is from Berton and Zibordi, and was the observations were taken in the Northern Adriatic Sea. So the point is now that we have to merge these two lines without introducing any discontinuity, which is not given by the field itself, but rather by the method. So what we do is that each pixel is to each satellite pixel is applied. They're applied both algorithms. Then the point is how do we distinguish between case 1, which pixel is case 1 and which other is in case 2. So we use this Mahalanobis distance parameter, which basically is a comparison of the single satellite spectrum with case 1 and case 2 in situ reference spectra taken from the Adriatic Sea in situ dataset and from the Mediterranean Sea dataset. So this parameter allows us to weight the single contributions of the two chlorophylls and to merge the final output. This method is from Dallemont et al. In 2003. So as an example, we see here that the Mediterranean is quite blue. So all the case 1 pixels are shown in orange and the case 2 in blue, and we can see that only has to do with some single spots close to the coast. This is the satellite image that we get when we apply the case 2 algorithm. Let's say the red curve in the previous plot. While this other one is the same satellite scene product when we apply the black curve in the previous plot. And when we merge them together, obviously you don't see so much difference apart from perhaps here in the Gulf of Godae, south in the Libyan Gulf. This is another example with the case 2 water being a bit, the area affected by case 2 water is being a bit wider in the North Adriatic, and where the contributions of the case 2 appears larger. So this is basically the output, the main output from the level 2 to level 3 processing. Now we move to the last bit of my lecture, which is level 3 to level 4 cellular processing. So the motivation is that several applications need complete data time series without any data host. These applications span from the assimilation into numerical models to the study of the ecosystem, to the ecosystem functioning, or to the monitoring and assessment of the status of the marine ecosystem. For example, in Europe, we have the Marine Strategy Framework Directive. The point is that the full exploitation of ocean color data is hampered mainly by cloud cover, apart from the other two issues, but mainly the cloud cover. As you can see here, the multi-sensor does increase the number of observations. This is a number of observations versus time over during last year over the Mediterranean. And we see that in black and green are the coverage from the two single sensors, Aqua and VIRS. And when we use the multi-sensor, there is an increase of about 20 to 25%. But still, most of the time, we have that the basin is only covered by 30 or even less percent. So we really need to fill these gaps in. But the point is without losing spatial or temporal resolution. And in order to do so, we need a data time series to get geophysical information from. So next slide will briefly present the interpolation scheme, which is based on the EOF technique. Interpolation means basically try to imagine what is the most plausible value for that variable, for that parameter in that precise space and time. And we use the climatology as a first guess for this value. And we use the climatology to fill the original level 3. This is the output from the level 2 to level 3 processing chain. We use the climatology to fill this image as a first guess to use to create the input image. This is the input image that goes into the data matrix used to build the level 4. So a time series of these input images is used to build the data matrix, which is then given to the level 4 processor. We need to balance the need of minimizing the time required to produce the level 4. So as soon as possible, let's say near real time, or but keeping the highest quality of the product as possible, let's say in reprocessed data. But so we have three different way of interpolating our data. In near real time, the data matrix is built such as each row which constitute the state vector corresponds to the single day image, so that the columns represent the pixel time series. The T0 is the most recent image, which is generally acquired the same or the next day as the satellite overpass, as I was mentioning before. While the delay time and the reprocessed data within these two other configurations, the input data matrix is built such as each row, rather than being a single image as before, it is made of a multiple subsequent daily images. And this configuration allows the temporal variability to be taken into account when computing the EOF modes. So this data matrix is given to the level 4 processor and is used to generate the level 4. So the data matrix enters the iterative EOF calculations, and at each iteration, the EOF patterns are used to fill the gaps in the original observations. until the variance explained by the current mode reaches the level of the noise. So we don't want to oversample our data, and so that to introduce the kind of salt and pepper effect in the output image. So this is the level 3, the original level 3 output from the level 2 to level 3 processing, and this is the output of the level 4. This is another example of a level 3 filled with the, this method generating the level 4. Now we want to let's say wondering if the method is reliable in terms of accuracy. This plot shows the both the level 3 in red and level 4 in black versus the in situ observations. And we see that we gain as much as 3 times the number of matchups with the level 4, with an enormous increase of number of observations, still keeping the same percent bias, the absolute percentage difference, with reducing incredibly the relative difference, which is the root mean square percent root mean square, pretty much having the same performance. And that's it. Yep.
My question is about the last slide. How did you manage to find another one? To find these hot spots near Egypt and Tunis?
This one, you mean?
No, Egypt, yes.
This one.
And Tunis.
Well, this is within here. Those images, those level 4 are from the delay time processing. So when what I showed you, the level 3 is this one, but I use all the variability which is in here and in here back to 10 days before, up to 4 days later, to build that image. And so all the variability which is included in this data matrix is then projected in terms of UF modes, spatial and temporal, to build the final level 4.
Okay, is that correct that these features were present when that was cloudy-free?
Of course, yes.
Okay, thank you.
Yeah. Yeah, that's what I was saying. We needed a data time series to get geophysical information from. Otherwise, we need to take the rabbit from the hat.
More questions? So your conclusion is that you really recommend this method, or you are really satisfied with the method of the dynamical interpolation?
I'm very satisfied, and yes, I would recommend this method for data interpolation, and need some fine-tuning depending on the scales of variability of your area of interest. UF modes, well, similarly to the optimal interpolation, strongly relies on the covariance matrices, and so which depends on the information you put in. But
have you done cross-validation with other data that you have when you have a cloud-free image and then you simulate that you have a cloud in that area and then trying to fill the gaps in that area?
Yes. Yes.
Okay, thank you. So we thank you, Gianluca.